delighted to introduce Professor Andy Woods from the University of Cambridge, who will be presenting on COVID dispersal in buildings, people movement and ventilation flows.
Yeah, thank you very much. My slides all up on the screen now? Good. So today I'm very pleased to be invited to speak today, and I'm going to talk about some work we've been looking at on ventilation and people movement in buildings and the impact on mixing the air and airborne aerosols. And this work really emerged from the RAMP group on looking at the role of people movement. And there's a team at the Institute in Cambridge. We've been looking at many of the issues of airflow mixing in buildings, and we've done a number of case studies. We've looked at collecting data at Papworth Hospital, some lecture rooms, library, concert halls, offices, and the museum inside the university, and trying to understand how you can adopt safe spacing strategies based on some of these results. And we've been combining measurements in buildings and also some laboratory modeling to try and predict infection rates. There's a number of publications already out and a few coming along. So just to set the scene, if we look at, so there's lots of data being collected recently looking at the distribution of droplet sizes when you breathe out. And if we look at these droplet sizes of order tens of microns and look at their fall speed, what we find is that the typical time for droplets of a few microns up to 10 microns to fall to the floor is of order 1,000 seconds, as Leora has just said in her talk. And so with those sort of timescales, these small droplets are likely to be transported by the air quite considerable distances before they settle out on the floor. Bigger droplets are going to settle out quite quickly, and smaller droplets may sort of be removed with the ventilation flow. And if we look at the Stokes numbers of these droplets, they're very small, and so they actually do get carried with the airflow. And so you know, we're looking at 5 micron or smaller droplets, and the contribution of that to potential infection transmission with the airborne mechanism as the vector of transmission. And it's interesting to note that droplets that you breathe out, quite a lot of it's volatile, but they don't fully evaporate. And so even if 90% evaporates, you're still left with a droplet with about 40% of the original radius that's not volatile and persists as an airborne aerosol. So to start off with, I'll just tell you a little bit about some of the data collected at Papworth Hospital. So at Papworth Hospital, we did a number of studies looking at individual patient rooms. And what we did is we'd release a pulse of CO2 as a tracer and then watch the way it decayed and mixed through the space. And so we had a series of sensors placed in a patient room. This is a plan view of a patient room. We'd released some CO2, and this is just showing the data of the concentration of CO2 that very quickly becomes well mixed in a matter of a few minutes, and then it gradually decays away with the ventilation flow. And in this hospital, the ventilation was a sort of top-down inflow, outflow mixing system. And so what you see is that, you know, to good approximation, most of the decay of the airborne aerosol will happen in a well-mixed space. And then we also had a look at some lecture rooms, and here's a lecture room we measured in one of the departments in the university. And this has a screen at the front and has air coming in through a mechanical ventilation system, and there's some other supply here, and then there's some extract vents here. And this leads to a large circulating flow, so a mechanical ventilation flow. But that large circulating flow ends up being very effective at mixing the air right through the space. And so we released some carbon dioxide near the front of the classroom where the lecturer would be, as if they were emitting CO2. And we had a series of sensors shown by these different colored objects. And what you see is that, you know, within 3 or 4 minutes, the CO2 mixed throughout the whole space. These are the sensors at all the different places in the classroom or the lecture room, in both cases along this walkway and also on the desks all the way to the back of the classroom. And so what you see is that there's this tends to be very well mixed, and so as a leading approximation, if we're trying to understand the risk of infection transmission, we can look at well mixed models. And so indeed, if you run a lab experiment in a water bath analog, where we supply ventilation air at high level and extract it at high level and add some dye in the supply air, or the supply water in this case. What you find is it mixes very thoroughly through the whole space. And if you then release a pulse of tracer, which would be like our CO2, you see it does actually get mixed up very effectively. And if we watch the decay time, it decays exponentially in time, as shown by this graph. So the simple idea of being well mixed does seem to happen in practice. And so as a very simple model of the infection risk, what we can assume is that there's a certain amount of airborne infection, the quanta of infection, the volume concentration, and this will be increasing in time because of the source of infection, and it decreases both because the ventilation flow removes that infection or because it settles out onto surfaces. And so there's a sort of quasi-steady regime gets set up within 15 to 20 minutes. And once we have that steady state concentration of infection through the space, we can apply a very simple Wells-Riley model to look at the risk of infection, which is really just a function of the concentration of the infection, the rate at which you breathe, and the time over which you're exposed to that. And so, if we pop this in with our data from that lecture theatre, which should seat 40 people, what we find is that, that we can work out infection risk. And you see actually if you stay in the lecture theatre for an hour, you start getting quite significant risk of infection, even with 5 or 10 people in the lecture theatre. And hence the need to actually reduce occupancy levels and increase spacing. But I think that the point here is that with a lecture theatre 15 to 20 meters in scale, the ventilation flows can mix these aerosols very thoroughly through the whole space. But there are more complicated buildings, and so we've been spending quite a time looking at complex buildings where the airflow patterns are very important in terms of understanding risk and safe spacing. This is the Seeley Library, which is in the history department in Cambridge. And this is it's an architectural prize library has this sort of a quarter of a pyramid type structure of a glass roof. And if we look inside, there's a series of workstations, and then this glazing goes up to this apex here. And the airflow comes in around this facade, you can see here, and runs through the stacks, the book stacks, across the working space, and then goes out through the top here. So there's a very complex flow pattern here with this. It has this glass roof, and we were measuring this in the winter, this last winter, trying to understand potential occupancy levels. So air comes in, there's heaters that heat up some of the air, but you get a net circulation pattern with air leaving, and then a circulation. And so we went and released some tracer, carbon dioxide tracer, both on the facade side, in the stacks, and also in the main working area where there are desks, just to see where CO2 went. And what we found very interestingly is that there's this net flow goes along from the stacks, from these inflow, and goes up through this region here. So if you release CO2 here, these spaces over here aren't really affected. But as you go towards the center of the library and up through the exterior to the exterior, that's where the CO2 travels. And so we were able to understand both the mixing across the space, but also the speeds of the convective flow in this ventilation. And from that, essentially, this is a cartoon of the flow path. We were able to work out how a release of CO2 here, a release of infection here would spread both across the flow path and along the flow path before venting out of the space. And so we came up with a little model to look at this diffusive advective transport. And from that, you can then get contours of infection risk at different places on the library floor. And so I projected this onto a floor map of the library. So here's the stacks, here's these working desks. And so a source here would essentially travel over here, and then it would convect upwards out of the library. And so from this risk map, we're able to work out the risk of infection for someone working on one of these benches based on someone working somewhere else. And what you find is it depends on the time that people are there, but also the distance from the source, as we'd expect. And so coming up with this model of cross-infection, you can come up with protocols for how long people should be allowed to work in the library until they need to leave. You can come up with the idea of working for a few hours and then emptying the library to let all the air ventilate from the library, and then basically remove many of those airborne aerosols and then start occupying the library again. So there's a number of simple protocols that you can adopt to actually come up with a sort of safe or a risk threshold that you're happy with. And we came up with a plan for people to work with these sort of this spacing given by these red crosses, which seem to satisfy some of the tolerance on appetite for risk exposure. Well, going back to Papworth, the other interesting aspect of infection dispersal concerns people moving through the space. And obviously in a hospital setting and other settings, there are many long corridors. And so infection can, people in the corridor may emit infection, and that'll travel, but it could also come from patient rooms and go down the corridors. And so we did some experiments releasing carbon dioxide in the corridor. And just when there's no one walking, just the air conditioning system led to an increase in concentration shown by these black lines. These are spaced about 10 meters apart, and it then decays. So you see, first of all, that the CO2 becomes quite well mixed along the corridor and then decays over a time scale of 10, 15 minutes. But if we walk up and down the corridor, and this red data shows someone walking every 30 seconds up and down the corridor, which isn't extremely busy, but what you find is that the CO2 persists a lot longer in the corridor, and so its decay time's a lot longer, but essentially because of the weight of people, and that acts to mix up the CO2. And just to compare this, if we have a very high ventilation rate in a corridor, so this is one of the very high ventilation rates, 15 air changes an hour, we find this is a picture showing distance and time, showing the concentration of CO2. It still spreads a long way along the corridor, 15 plus meters, but it decays very quickly. Whereas if we have a poorly ventilated corridor, which was in the old Papworth, the tracer persists for a very long time, over half an hour, and spreads much further down the corridor. And so the effect of people moving is very important. And so we carried out some experiments to try to quantify the diffusion coefficient or the mixing coefficient associated with people moving by essentially moving a cylinder through a water bath, a channel where we had some dye, and we watched the way this dye spread out as a result of a number of paths of people walking up and down the corridor. And you'll see here on this movie, the cylinder moving back and forth, displacing this dye. So we're able to get real data here using image processing. And from that data, we're then able to look at, so here's the dye spreading out down the corridor. We could measure that, and we were able to look at how the concentration spread in time and show that it was a diffusive process, and we got some diffusion coefficients. So this is looking along the water tank, and this is the cylinder going back and forth with time. And what you can see is how it spreads cross channel with time, and it depends on the rate at which the frequency and the speed of the cylinder. And then we added some particles to the cylinder, and so now we have a ventilation flow going from left to right, and we have a suspension of particles here. And what we see is the blue is particle-free clear fluid. So this is the actual photograph on the top image, and the lower image is false color. And the red is the particle-laden fluid, and you can see that the cylinder acts to stir up the particles right through the depth of the cylinder. So even though they're sedimenting, they remain very well mixed vertically. But the fresh air coming along here is trying to replenish that aerosol or that particle-laden air, but there's a big mixing zone that forms because of the weight-driven mixing. And so even with ventilation flows, people walking can lead to this increased residence time in the space. And so motivated by that, we're interested in looking at the risk of infection associated with this. And so you can envisage in a hospital setting, if you leave a patient door open, infection may come out of the patient door and run along the corridor. So we did some experiments looking at this, and so here we released CO2 in the corridor, so it was a source of infection in the corridor going into a patient room. And what we found is that as the door opening time increased, the amount of CO2 or a proxy for infection would increase inside the patient room. And so you can actually come up with the risk model, the risk of infection as a function of the time the door's open, and as a function of the distance from the door. And because of the mixing, the distance from the source to the door isn't actually that critical. It's the actual time of opening that's very critical. And these become quite significant risks if you're dealing with all the different patient rooms, 40 or 50 patient rooms down a corridor, each of which is open 4 or 5 times a day. Actually keeping them closed most of the time and having very rapid in and out into the door and not leaving them open becomes very important in terms of controlling the risk of infection. And we measured this flow through the doors, and it becomes, when the doors are open, it's a very significant exchange flow, as big as the background ventilation flow. And we can apply the same ideas to look at what happens in tube tunnels or in supermarkets to try and understand the mixing. So imagine someone's walking along an aisle or walking along a tube tunnel, and they might be coughing out or breathing out aerosol. And as they move, that's going to get dispersed by the presence of other people moving along the corridor. So you have this moving source of aerosol, and the wake behind them will gradually be ventilated, particles will gradually settle, reducing the concentration. And so if we have a moving source of infection, and we look at a dispersion, ventilation, and a settling of particles, we can combine that with our risk of infection based on the exposure and duration for someone walking behind that person, like in a tube tunnel or perhaps going down a supermarket aisle. And from that, we're able to work out the risk of infection. And just as a simple example, if we have 1 in 100 people infected, which I think was at the height of the pandemic, and we have 10 to 20 shoppers in the wake of a shopper who's infected, or in a tube tunnel, you might have 100 or 200 commuters in the wake who are actually going to see the wake. If you look at over the whole country, if we have 1 million people, I think 2 million people commute on the tube, and if we have 1 million people shopping each day, then that may end up with these risks end up being 10 to 100 people infected per day. And so you can begin to understand some of the risks associated with these different transmissions. So really, just to summarize, small aerosols are transported and mixed by the airflows, dispersed significantly by movement of people, and they have residence times of tens of minutes. And in order to reduce exposure to these aerosols, I guess, and this is what we've been doing, limiting occupancy numbers, limiting interaction times between people and buildings, so having single occupancy or very limited occupancy, wearing face masks, of course, and then increasing the ventilation rate, which reduces the concentration of the infection. So, and these principles have been used to come up with risk models for a number of these buildings to help inform how we can start reoccupying some of these buildings, particularly in the university. So I'm happy to stop there and take any questions.
That's great, Andy. Thanks very much. We do have a couple of minutes for questions. There's one comment in the chat so far saying, great work on the quite fast mixing. We did assume that in our quantitative microbial risk assessment. And then there's a link to a paper which was published in Environmental Health Perspective.
Yeah, I mean, it's been very interesting actually looking at these more complex buildings. I mean, so we've looked in some of the museums in Cambridge and the libraries and also the concert hall, where the buildings aren't well mixed, and you need to have a sort of more detailed understanding of how the air moves around to actually understand the infection risk from one person who's a source to other people in the space.
Great. Another question has just come in from Eora, saying the case studies you have shown are really interesting. Thank you. Are you assuming there is no safe concentration of virus particles in the air?
Sorry, could you say that again?
Are you assuming there is no safe concentration of virus particles in the air?
No. So I suppose what we've been doing is looking at this sort of Wells-Riley, which is the sort of model people have been using to look at the risk, modeling it as a sort of Poisson process. We're modeling that risk, and then based on the number of particles in the air, and I guess then there's a decision that the people who run the building or the university or the museum authorities, or in the case of offices, the people running the offices have to set a threshold risk level which they're prepared to tolerate in order to allow occupation. So some of the teaching labs where there's many parallel benches have had they're trying to do demonstrations. The question is, what's the safe occupancy level? Well, I think you have to decide what risk threshold you're prepared to accept. Is it 1 in 1,000,000, 1 in 1,000, and then from that you can make a model up based on assumption of the number of people who might be infected and where that infection goes. I mean, I think in the supermarkets again, when we're at the height of the pandemic, if a fraction of the people who went shopping were asymptomatic but infected and emitting aerosol, you wouldn't know. So there would be a risk, and I guess this provides a mechanism to try and understand what that risk is or what risk would be.
Thank you. Questions are coming thick and fast. I think we've got time for for one more, and I'll do it in the order that they came in. What do you expect from air humidity?
Air humidity?
Yes.
Well, my goodness, I'm not quite sure what the question's implying. I mean, I think if you're supplying air with a different humidity from, so the air conditioning system could be supplying either dehumidifying or humidifying the space, that may lead to some density contrasts in the air coming in, which may impact the way the mixing occurs. If it's looking at, do the aerosols become scavenged, or do they change because of the humidity levels? I'm not sure about that. I haven't looked into that question. But I guess the aerosols do evaporate, and so I guess the drier the air, the quicker they'll evaporate. But I think the evaporation time with these very small drops is extremely fast, so that's not really a rate limiting factor in the modelling we've been doing.
Okay. Thank you very much. There are further questions, but I'm afraid not.
So, Joanna, can I interrupt? I mean, we did have to cancel a talk, and so the breakout sessions have been expanded. But I think if you wanted a few more minutes to discuss the specific questions in the chat to Andy, I think you should do that.
Good plan. That's okay with you, Andy? We'll quiz
Yeah, that's fine. Yeah, absolutely. Yep.
Is it easier if you read the questions yourself, or do you want me to read them out to you?
Hang on. Question and answer. Oh, I see. Okay. So I've got, will CO2 get, so stop, will CO2 gas and smaller sized particles diffuse similarly in the air? This is an anonymous attendee. So yeah, that's a very good question. The smaller sized particles will move with the air, but they do gradually settle. But the settling time is, as I mentioned at the beginning, it's of order 1,000 seconds. So that's much longer than the typical travel time of the air over several meters in the flows in the space. And so I think having a dilute CO2 gas as a tracer is a good model of that. Of course, if the CO2 is too concentrated, the CO2 itself has a different density and will actually move as or the buoyancy of the CO2 will affect the flow. But as long as it's sufficiently diluted, I think one is a good proxy for the other. Ed Gallia, when you measured CO2 levels, how did you take into account background CO2? Oh, so we have a series of sensors which we've calibrated the background CO2 levels. So we'd typically set all the sensors in a row, get a background measurement, and then look at the measurement relative to background. And then at the end of the experiment, we'd recheck them to check that we still got the same reading for the background. Some of the CO2 sensors are quite sensitive, and they can sometimes drift, but we try to ensure that in the sort of good data we were collecting, the sensors were giving reliable measurements, really by calibrating before and after on background levels. The experiments take a long time, so after each release we leave the experiment for 40-50 minutes until the sensors had returned to background. Why not make a design of buses with windows just in an air duct? Oh, that's
that was earlier.
To expect air humidity. A new design of corridors is needed in the future, or new airflow in corridors. So corridors, we obviously need corridors, but I think it's, if we ventilate the corridors well, we can limit the transmission from corridors to individual rooms. And so I think with a sort of hospital design or an office or other building, you really want to keep the doors shut so that the offices can ventilate themselves and are separate from infection which may move down the corridors. So within the corridor, single release. So if someone walks down the corridor and leaves, then that single release is going to be ventilated away on a ventilation timescale. It's just that if someone in the hospital environment, often there's nurse stations and so on in the corridors, and so they'll be impacted by any infection coming out of patient rooms into the corridor. So I think there's simple protocols. So at Papworth, we recommended some simple changes in protocols. So when people go to have drugs delivered to them in their room or other things, the idea now is that the door isn't wedged open, as sometimes happens, but the person goes in and then shuts, or if a doctor goes to visit a patient, they go in and shut the door after them, and just make sure that the amount of time the door's open is actually really limited. and the other thing we instigated is that the rooms and the patient rooms have individual temperature control at Papworth. And what we found was as that temperature started changing relative to the corridor temperature, the rate of exchange flow dramatically increased. And so another recommendation was that we try to keep the patient rooms at the same temperature as the corridor, which really reduces that exchange flow rate. It's a factor of 10 almost when the temperature increased by 2 or 3 degrees. Let's see, any idea in terms of gathering outdoor sports? We haven't really looked outdoors. I think outdoors there's a lot more background flow and mixing, so that the rate of dispersion is much faster. Have you found any other parameters, humidity, temperature, have a role in promoting or restricting airflow mixing? So that, I mean, there can be dead zones in spaces depending on the design, and so I think the location of the inflow and the outflow vents is extremely important, and in many ways it's the detail that really matters. But obviously there are buoyancy effects, and so sometimes the placement of heat radiators or other heating or cooling systems can actually have a profound impact on the structure of the flow and density stratification in the flow, which can then lead to particular transport pathways for the air, and hence the aerosols. I think a lot of the work on natural ventilation, looking at the development of two-layer stratification and in displacement ventilation, those sort of effects are very important in terms of actually understanding the distribution of airborne aerosols. But in air-conditioned or mechanically mixed buildings, you see some quite similar patterns. But the other thing you see a lot of is very strong lateral flows through spaces, which can lead to very rapid transport. And so some of the safe spacing distances, we certainly saw things traveling 10 to 20 meters in spaces at tens of % of the initial concentration, so before decaying. So I think the detail of the flow is very important in terms of where the risks are from particular locations of sources. I was at a PSW meeting, and if I remember correctly, the designs doesn't consider the aerosol fact. Oh, I don't know what that is. I think is that all the questions, or are there some other questions?
That was the final question. Thank you very much for agreeing to answer more, and I think that's a great idea, Mike. Thank you. So thank you so much to our speakers, Andy and Leora. I think they were both really fascinating presentations. I'll now hand back to the Newton Gateway, who will outline how the breakout session will work.